Hi everyone, this is the second part of week 1's lecture. In the last lecture, we talked about the difference between the descriptive statistics and inferential statistics. And today we'll discuss more in depth about the descriptive statistics. We have 3 different descriptive statistics here. The first one is the one that measures central tendency, such as mean, median, mode. The second one that we have is the one that measures the dispersion, such as variance and standard deviation. And the third one is the one that measures the linear association between 2 variables, such as covariance and correlation coefficient. These measures are called statistics if it's calculated from a sample, but it's called parameters if it's calculated from population. Also note that we use different notations depending on whether we're talking about parameter or statistics. So here, when you're talking about the mean or average of the population, we use the Greek letter mu. And if you're talking about mean or average from a sample, then we are using the letter Y bar. Similarly, if you're talking about standard deviation from a population, then we use this Greek letter sigma. Whereas if you're talking about sample standard deviation, then we use this letter or notation S. Let's talk a little bit about the central tendency descriptive statistics. So the first one is mean or average. And again, we use mu when we're talking about the population mean. And then we use Y bar when we're talking about the sample mean. Here's the formula for calculating the population mean. So it's what you already know. It's calculating average, so adding up all these observations and dividing by the total sample size n. And to calculate the sample mean, you do the same thing. So when you have a sample, you add up all the sample and divide it by the total sample size. So in order to calculate the variance or sigma square y, or in population variance, or denoted as S square y, when you're calculating variance for the sample, you have these 2 different formulas, which look pretty much the same, except for the population, you divide it by n, and for the sample, you divide it by n-1. In order to calculate the population variance, you subtract the population average or population mean from each observation, and then you square them and you add all of them and divide it by the total sample size. For the sample variance, you do the same thing, except for now you're dividing by n-1. For the standard deviation, it is just square root of a variance, and it's denoted as sigma y or sy. So basically, once you calculate the variance, you just square root the value, and that will give you the standard deviation. Here's some empirical rule that may come in handy later. So basically, what the empirical rule says is that when you have a sample of measurement that has a symmetrical mound-shaped distribution, in other words, normal distribution, then you have this rule. So if you're 1 standard deviation away from the mean, then all of this area underneath the mound contains about 68% of all data points. Similarly, if you're 2 standard deviation away from the mean, then all of the area under the curve contains 95% of the data. Remember that the area underneath this curve usually adds up to 100%. Next, we have skewness and kurtosis measure. These two measures give you information on the shape of the distribution. So here's the formula for calculating skewness. You generally will never have to calculate these by hand. Usually, whatever software program that you're using will generate these for you. And the skewness actually is a measure of how symmetric the distribution is. And if the skewness is 0, then the distribution is symmetric, like a normal distribution. And whether it's positive or negative tells you whether it's long right or left tail. Kurtosis gives you how big of a tail you have, and basically gives you probability of large values. So if kurtosis equals 3, then it's a normal distribution. If it's greater than 3, it means that it has heavy tails or thick tails. So here we have an example of 4 different distributions. The first distribution is a normal distribution where we have skewness of 0 and kurtosis of 3. The graph B shows that skewness is 0, meaning that it's symmetrical, but kurtosis is larger than 3, which means that it has thicker tails, as you can see compared to the ones compared to the normal distribution. Distribution C shows that the skewness is negative, which means that it has left tail. And kurtosis is 5, which is greater than 3, so it has thicker tail. And then the last distribution, the skewness is positive, greater than 0, which means that it has right tail. And kurtosis is again greater than 3, which means that it has a thicker tail. To look at the relationship between two different variables, you have several different measures. The first measure that we are going to look at is called covariance. Say you have a random variable x and y that have some sort of a joint distribution. The covariance between x and y is calculated by having an expectation of x minus mu x times y minus mu y. If you're trying to calculate the sample covariance, then you'll replace sample average y bar x and sample average y bar y instead of mu x and mu y. So the covariance is a measure of linear association between x and y. When you have a covariance that's positive, it means that there's a positive relationship between x and y. In other words, when x increases, y also increases too. If covariance is negative, it means that it has a negative relationship, which means that when x increases, y actually decreases, having an inverse relationship. If x and y are independently distributed, then covariance xy is equal to 0. But this is not the case the other way around. So just because you have covariance x and y 0 doesn't mean that you have an independently distributed variables. And we'll see an example of this later. One thing to note is that if you have a covariance of itself, so if you have a covariance of x and x, then by the formula, you get a variance of x. The problem with covariance is that it gives you the relationship, but it doesn't give you how strong these relationships are. So if the covariance is positive, then we know that it has positive relationship. And if it's negative, then we know that it has negative relationship, but we don't really know how strong the relationship is. So that's when you calculate the correlation coefficient. Correlation coefficient, the way you calculate is that you divide the covariance of x and y by square root of variance of x times variance of y. Again, you don't ever really have to calculate this by hand because the software program would calculate this for you, but you need to understand what this means. So correlation coefficient usually ranges between -1 and 1. And as you get closer to 1, that means that you have perfect positive linear relationship. Whereas if the correlation coefficient is -1, then it shows that you have a perfectly negative linear relationship. Again, if the correlation coefficient is 0, it means that there is no linear association. Here are some examples of correlation coefficient. Remember, the correlation coefficient measures the strength of linear association. In other words, it measures how close the dots are to the straight line. And as the dots become closer to the straight line, then it gets closer to the +1 or -1. If you look at graph 1 or graph A, the correlation coefficient is 0.9, fairly close to 1 because most of the plots are close to a straight line. The second graph, B, the correlation coefficient is -0.8. It's negative, so it's downward sloping, or the variable x and y have an inverse relationship. And it's pretty close to 1 because most of the dots are still pretty close to the straight line. Graph C has correlation coefficient of 0 because dots are all spread out and it cannot fit into a straight line. And then the graph D has a correlation coefficient of 0 because, again, you see that there is a quadratic relationship instead of a linear relationship. So this is the case where the correlation coefficient is 0. That doesn't mean that there is no relationship. There is a relationship, it's just that it's nonlinear. Here are more examples of correlation coefficient. This is just to reiterate the fact that correlation coefficient is not about the slope, but it's about the strength of the relationship. In other words, you can see that it's not about the slope of the line because you can see that the lines, as it gets less steeper, the correlation coefficient is still 1 because all the dots are on a straight line. And then as the dots get more and more spread out, the correlation coefficient actually declines. Going back to our original empirical policy question, we are interested in if smaller classes are related to higher test scores. Here we have a scatter plot of test scores on y-axis and student-teacher ratio on x-axis. Do you see any linear relationship? Can you fit positive or negative line through this? When you calculate the covariance between test scores and STR, it gives you a negative number, meaning that there is a negative relationship between test score and student-teacher ratio. If you try to calculate the correlation coefficient, it gives you -0.23, meaning that not only is a negative relationship between test scores and student-teacher ratio, but it's actually quite far from -1, meaning that the relationship is very weak. We can also see that from the scatter plot. We see that all the dots are very far away. Maybe you can fit a line that's negative, but all of the dots are really far away from the line rather than close to the line. So we know that the linear relationship is very weak.